Hello everyone, my name is Kaan Tekelioğlu and this is my magnetic resonance imaging final project. So on my project, I chose the selective excitation topic and I focused on three different concepts. The first one is the refocusing gradient area. Second one is the adding and offsets to the magnetization. And third one is the modulating RF pulse. So first I will show you my code without any refocusing, offset or modulation. I started by setting the variables, the time for 6 milliseconds. I initiated the RF pulse as a sync. I set the gradient without any refocusing area. And I also created an arbitrary position vector for slice selection. I set the relaxation times same as the values given to us in the homework. T2 relaxation is 100 and T1 relaxation is 600. So in my code, I initiate the signals, the magnetization, and start slice selection. For each specific position from 1 to 400, I calculate the magnetization. I also take into consideration the T1 and T2 relaxation times. I also find the RF rotation, and finally from the AM plus B formula I find the magnetization. So I will run the code really fast and show you the output. So this is the gradient. As you can see, it's 0.1 constant as we have no refocusing. This is the RF pulse I gave. This is the MZ profile, phase profile. As you can see, currently it's out of sync and there is a lot of phase dispersion. And this is the magnitude profile. So as I set the RF as a sync pulse, it was expected that the magnitude profile seems similar to a rectangle. So for the second part, I would like to show you what I did with the refocusing gradient. So normally, when we give the RF pulse, we start to set the gradient Gx, and then we give a negative gradient. The book says that this gradient time should be about half of the gradient time. Now the reason behind this is, if you try to read the signal without giving this negative gradient, the phase dispersion is so large that you can't read the signal. The signal power is too weak. Now the book says that the timing of this negative gradient should be half of the gradient, but this is just an approximation. They say this because they assume the RF pulse is a very narrow sink. Now I will try to find the perfect value for it. So for this, I took the code that I just showed without any refocusing, and I added a loop to it very simply. So for values starting from 0 to 1 with 0.01 increments, I found 100 values. Now, what do I do with these 100 values? So the phase profile looks something like this. So what I'm trying to do is to take 2 points between these two max values and try to flatten this line out as much as I can. The more constant, more linear I can make this line, the better. This means phase dispersion decreases. Now, when I run the code, it calculates phase profile for 100 values. Between these values, what I do is I find the phase of the signal. I take the point from the index at 100 and I take a second value from the index at 300. These values are inside the max values, so I can flatten the line between them. I find the average angle between these 2 points and I take the difference of the angles for all the values between these 2 points. Then finally, I find the minimum index in this 100 value angle difference vector. The value that minimizes this is the best refocusing gradients.
The code is rather long, so I will speed it up.
So as you can see, now I've added the refocusing gradient. Our initial gradient was 0.1 for 6 milliseconds. Now it goes to 12 milliseconds, and as you can see, with the best refocusing gradient, the value should be minus 0.52. I worked on the offset frequency. Now, when I add an offset frequency to the magnetization, I expect that the phase profile, magnitude profile will shift, because changing the frequency of the RF pulse or the adding an offset is how we choose the slices in the first place. So for this, I add the variable called df. Now, initially, this variable is 0. So I calculate everything normally, as I showed before, without any offsets. Now, in order to find if the profile shifts or not, I needed the initial values. Then, I added an offset vector, starting from 500 to 10K. This is, of course, in terms of hertz. So, for values starting from 1 to 20, I choose values inside this vector and set it to df. So, I find 20 different values for 20 different frequencies, offset frequencies. And what I do is, I find the from the magnitude profile, I found the maximum value of the signal without any offsets and set it to max signal index. Then, for each of the 20 values, I found the maximum value from the magnitude profile from signal offset added and take the maximum signal offset index. When I subtract these two values and divide to 10, I actually find the shift in millisecond scale. So now I will show you.
The loop will run 20 times.
So the plot with the orange lines, as you can see, is the original signal without any offsets. As you can see, its middle point is at 0. And the signal with blue lines is the signal with 5 kHz offset added. As you can see, the signal shifted left. The phase profile also shifts. Finally, I would like to show you that the plot of the 20 values, 20 different offset values, frequency versus shift. As you can see, up to certain points, frequency and shift move linearly. At certain points, you see jumps. The reason behind this is that my position vector is actually not long enough to compensate this kind of shift. So if you try to shift beyond a certain point, it just flips. Finally, I am modulating the RF pulse that I initiated in the beginning. So, modulating the RF signal, I expect that there will be a shift in the slice profile, just as adding an offset. So for this, I first ran the code without any modulation, as I did before. I find normal values. Then I added a variable with an exponential, pure exponential. This is what I modulate the RF signal with. And as you can see, the frequency inside it is a variable as well, mod val. So this mod val ranges from 25 Hz to 500 Hz. There are 20 values inside it. So for these 20 values, I find the magnitude profiles, shifted magnitude profiles. Then, similar to what I did with the offset, I find the max of the signal, original signal, and the max of the modulated signals. I subtract the indexes from each other and divide to 10 to turn it to millisecond scale. And
as you can see, I will now show the results.
so here you see the shift versus frequency. So I expect that these lines were linear actually. They are not. I expected that they would be. Probably the reason behind them is similar to the previous one. The shift is much higher with modulation, not like offset. So perhaps my position vector is once again not enough. So you see jumps here. For certain intervals, the frequency and shifts are linear as expected, but for some values there are jumps. Gradient versus time is of course same. This is the RF versus time. This time, as we multiplied with a pure exponential, you see the imaginary and real parts, and of course the absolute one with the yellow line. This is the MZ profile, phase profile. So as you can see, phase profile is completely changed. This is because of the exponential. And this is the magnitude profile. So as you can see, the shift is this time to the right. This is because there's a positive frequency inside the exponential. Thank you for listening.